Our group is the Sea Life Safe Propeller team. First, we'll cover some background on our group and project. Our team consists of Sarah McKinley, the team lead, Daniel Lynch, Matthew Rose, Matthew Shipton, and Devin Weaver. The main objective of our group is to protect sea life from being harmed by boat propellers, with a secondary objective of keeping objects from being entangled in the propellers. We intend to solve these problems by putting a mesh over the propellers. Our key question is, how much thrust is lost by placing these meshes around the propellers? Our project was inspired by Spineless, which documents the negative impact of propellers on sea life. No prior work using the solution was found when researched by our group. Our project is significant in its goal to protect sea life, as evidence shows many forms of sea life suffer from boat propellers. Young fish suffer high mortality rates, and adult sea creatures can be seen with wounds from propellers. Our solution will help protect these sea creatures.
In order to test the loss of thrust of a propeller through a mesh, we needed to develop a procedure and apparatus that could give us a force output with the propeller mounted under the water. To test, a procedure had to be developed. Firstly, the apparatus was needed to be set up. Our apparatus can be seen on the next slide. Next, once it was set up, the mass of the motor and propeller was taken. This was done to record a baseline to ensure the measured values were only the thrust force. We also then took a control force with no mesh attached to the motor. We then attached meshes to the motor propeller and ran 5 tests each, turning off the power supply each time to allow it to settle. Each time the power was supplied, the force was recorded. All of the data was then aggregated and analyzed. On this slide, our experimental setup can be seen. We used guide rods mounted to the bottom of the bucket to ensure that the propeller was constrained to only be able to move up and down. This ensured that only the force from the propeller was being read and the propeller wasn't moving around in the bucket. The output force was read using a spring scale attached to the propeller and mounted above the bucket. We were able to swap out the meshes pretty easily. The relevant variables in this experiment were the thrust, the mesh size, and the propeller speed. The thrust was the dependent variable. The mesh size was the independent variable being changed, as that was the goal of the experiment. The propeller speed could be considered another variable, as it would affect the thrust force, but it was held constant by using a battery that applied the same amount of wattage across each test. The measurement technique we used to measure the force was using a spring scale attached to the propeller motor mount and reading the force output. For the testing equipment that we needed, this is the list. It's pretty self-explanatory, but the biggest things on the list were the propeller, motor, thruster, the meshes, and the battery. We also had a backup power supply in case the battery were to fail. We also needed to 3D print the mount for the propeller and meshes to be used in our apparatus.
Our schedule goes as following. On 2/16, we wrote the initial project proposal. On 3/2, we wrote a detailed test plan. On 3/23, we finalized the test plan, reviewed risk assessment with the TA, and sent the TA the list of materials to purchase. On 4/6, we ordered and acquired materials, began to test individual components, and print the 3D necessary parts. On 4/20, we verified individual component designs, assembled the system, and began testing. On 5/5, we began analysis of the test data and started writing the final paper and also completed the viscosity lab. On 5/6, we completed the error analysis of our experiment, finished the final paper, and recorded the presentation. So our budget consisted of meshes that in total cost $53. The motors and propellers we bought were $26.45. The batteries we used were $27. The wooden dowels were 99 cents. The electronic speed controller was $17, and the epoxy was $7. So after doing a risk assessment, we determined that there was overall a low risk. The two main things we were worried about was electric shock. We made sure to use waterproof equipment and to turn off electricity immediately after the trial ended. The second thing we were worried about was cuts and scrapes. So we made sure to keep body parts out of the testing apparatus and use containers to make reachable propellers difficult.
We will next discuss our results. 5 trials were performed with each mesh size, which were then averaged in order to determine the average net thrust shown in the right-hand column of the left-hand table. These data were then used to generate the plot at right. And while mesh size is typically referred to by the number of holes per inch, we have presented the data here as mesh hole size as a percentage of propeller diameter for easier trend visualization. As shown, larger holes resulted in less thrust loss, as expected. The minimum thrust lost was 20%, with a maximum thrust loss of approximately 45% when compared to the control thrust. From the previously shown data, we can determine that no matter what mesh size is used, a significant portion of the thrust produced is lost. Smaller mesh sizes yield even greater losses, as expected. With regards to an uncertainty analysis, a design stage uncertainty analysis was not performed for this experiment, primarily due to time constraints. The final uncertainty analysis presented here is incomplete, as much of the data about the measurement instruments needed to complete the analysis was unknown. However, the zero-order uncertainty of the spring scale was determined to be 0.05 newtons, and a value of 0.1 newtons was assigned to the systematic error at a 95% confidence level. This value is assigned by judgment, as empirical data for determination of the value were not available.
Next up is conclusions. Based on our data, there is at least a 20% loss of thrust from placing a mesh around the propeller. With smaller meshes, there was even more thrust lost. So based on those numbers, using a mesh around a propeller does not seem to be a viable solution to protecting sea life from these propellers. We had quite a few potential sources of error in this experiment. First, we used a spring scale to take our force measurements, which was not the most accurate way that we could have measured the force. We also had some issues with our motors burning out and the battery power being drained, so that may have caused some inconsistency between tests. We're also doing testing in a 5-gallon bucket, so there may have been impacts on the fluid flow from having walls so close to the propeller. And finally, we're using wooden dowels as our guide rod to ensure that the propeller moved straight. But we noticed throughout testing that the dowels seem to absorb some water and get a little bit thicker, so that made our propeller stick a little bit on the guide rods. The next step for this project may be to repeat a similar experiment using better equipment in order to validate our results. This experiment could also be run with a larger propeller to see if everything scales up as expected. And also, since our results did indicate that using a mesh would not be an effective solution to this problem, we would also recommend that other groups explore alternative solutions to protect the sea life. We would like to thank Professor Hoover and our TA Matthew Turner for their assistance with this project, as well as Julie Bearwald, who wrote the book that was the inspiration for the project.